In this video, I'm going to do some exercises involving exponential growth and decay with general exponential functions. So here we go. First, this is about radiocarbon dating. The half-life of carbon-14 is 5,730 years. A sample from an archaeological site is found to have 76% of its original carbon-14 content. How old is the sample? Okay, so first, a little bit of context. Radiocarbon dating. How does this work? Okay, well, here's the Earth, and there's an atmosphere around the Earth, and in the atmosphere is a lot of carbon dioxide. Most carbon, normal carbon, is of a type called carbon-12. What that means is that it has 6 protons and 6 neutrons in its nucleus, and then it has it has 6 electrons bound to it for chemical reaction purposes. Carbon-14 has 6 protons, but it has 8 neutrons. The protons still attract 6 electrons, so chemically carbon-14 is identical to normal carbon, but it has those 2 extra neutrons in its nucleus, and it will spontaneously break apart because it's unstable to have that many neutrons in the nucleus. So carbon-14 undergoes radioactive decay. It has exponential decay, with a half-life, I can go ahead and call this T sub h, equal to 5,730 years. Now, where does carbon-14 come from? If it keeps breaking down, then sooner or later we should run out of it. Well, the source of carbon-14 is that high energy radiation just from out in space can come in and interact with, actually it interacts with nitrogen. So normal nitrogen has 7 protons and 7 neutrons, but these high energy high energy cosmic rays can come in and interact with a proton and turn it into a neutron. So an ordinary nitrogen nucleus can be turned into carbon-14. Eventually, the creation process that happens at some particular rate comes into equilibrium with the decay process. And so, for the most part, the ratio of carbon-14 to carbon-12 in the atmosphere is constant, more or less. There are complications with this. The incoming radiation from space does change a little over time, and also human activity has upset the carbon balance. So whenever we set off a nuclear bomb, that throws some extra radiation into the atmosphere, and it throws the carbon-14 balance out of whack. So there's more to it than what I'm telling you, but this is the basic idea. Now, given that there's this equilibrium ratio of carbon-14 to carbon-12 in the atmosphere, well, green plants, of course, let me draw a little tree here, bring carbon from the atmosphere in. They take in carbon dioxide and incorporate it into sugar and other elements of the organism structure. And then other animals eat eat the trees. So let me see here. I don't know. How about let's draw an elephant eating the tree. And then other animals eat those animals. So we'll draw a lion here that eats the elephant. And what happens is that over time, all organisms that are eating plants develop the same equilibrium ratio of carbon-14 to carbon-12 in their bodies. Now, as soon as an organism dies, that ratio starts to change because they are no longer ingesting fresh carbon. Any carbon-14 that was already in the body is going to decay without being replenished from prey, from trees, from other plants, from the atmosphere. So what that means is that if you know what the equilibrium ratio of carbon-14 to carbon-12 should be, and you can find a bit of organic matter, so wood or maybe some seeds or some food residue, you can look to see how much of the carbon-14 has decayed. So here we go. Let's say that you're looking at a tree and you're looking at the ratio of carbon-14 to carbon-12. It'll start out at that equilibrium value, and it'll stay that way as long as the tree is breathing. But then when the tree dies, the remaining carbon will decay exponentially. So then if we then do archaeological find and we find an artifact that was made from a piece of wood, then we can look for its carbon-14 content and get an estimate of that time based on the properties of carbon-14. So here's how to set that up. I'm going to set time equal to 0 here, and then I'm going to let time be big T right now. The information that we are given says that the half-life of carbon-14 is 5,730 years. Okay, so half-life of carbon-14 is TH 5,730 years. We are also told that the sample has 76% of its original carbon-14 content. So again, what's happening is that we know how massive the fragment is, we know what this ratio should be, and we've determined that, and I need to draw this a little bit less extreme, that from t equals 0 to t equals big T now, it has dropped down to 76% and keeps going. Now I will give you a quick warning here. This particular problem says that 76% remains. Some of the problems in Hawks will tell you that such and such percent has decayed. You have to be careful because for the 76% that's remained, that means that this is the point that represents now. The other way that you might see this expressed is that 24% has been lost to decay. So read the problem carefully. I drove myself nuts one day trying to figure out why we weren't getting one of the Hawks problems right, and it's because I was misreading that particular part of the statement. So here's exponential decay. Well, let me put this in right here. Now, I'm going to first divide by q sub 0 to get to here, and use the fact that when little t equals big T, q over q0 is 76%. Right, that says that the remaining amount of stuff q compared to the amount that the sample must have had originally is 76%. So that allows me to write, and I'm going to write it in decimal as 0.76 instead of as a percent, is equal to e to the minus k times, and I'll put in big T because that's for now. We need to solve for what time is now, given that time 0 is when the tree died. So we need to solve for big T. Well, we've done several problems like this. There's an unknown up in an exponent that we need to get. How do we undo this exponential operation? We'll apply ln. Okay, so ln of the left is 0.76 is equal to ln of the right, e to the negative k times t. And as I've mentioned, the key point here is that ln is the inverse operation to the natural exponential, so ln of e to stuff simplifies down to just stuff. That means this right-hand side can be simplified nicely. The left I'll leave as ln of 0. Nope, that should be 0.76, sorry. And where were we? On the right, that should be negative k times t. Now to isolate t, we just divide by negative k. So that will leave us with t equals ln of 0.76 divided by negative k. But now maybe you're thinking, what do we do with this k? The problem gave us some information, but it did not tell us specifically what the rate constant was. Well, it didn't give us the rate constant, but it did give us the half-life. So k is not the half-life, but it can be found from the half-life. Okay, so remember, let me come over here and do this. Remember that the half-life is equal to ln of 2 over k. And you can also write this the other way. K is ln of 2 over the half-life. So since we were given that the half-life was 5,730 years, we can use this formula to find out what k is. It's just that k is going to end up being a clumsy decimal number. So even if you've solved for k as an explicit decimal approximation, it's usually better to just remember that k is known and do all of your calculations over here with the k as k rather than try to write down that clumsy decimal number all over the place. Okay, well, let's go to the calculator. I need to calculate k. So I'll type a fraction and do ln of 2 and divide by 5730. Now, I want to do something else with this calculation, so I'm going to store this, and I'll be uncreative here and use memory k to store it. So again, what I did there was I typed the calculation ln of 2 divided by 5,370. I hit the store button to create that little arrow, and then I hit the alphabet button, and then the k is right there over the parenthesis key. So when this is done, the number has been calculated and it's stored in memory k, and so for example I could get it to calculate k, just recall it from memory. Remember also, this is the calculator's power of 10 scientific notation. So 1, 2, 3. That's shorthand for 1.2096 times 10 to the negative 4, which is that you would have 1.2 to start with and then hop the decimal point over 4 times. So that's what that notation means. Now getting back to the problem, we want to answer the question, how old is the sample? Which means that, again, we're interested in what time represents now, because we set up time 0 to be when the tree died. And so this t is the age of the sample. Okay, well, we solved for t in terms of k like that. So now all we have to do is use the calculator. We found that k was approximately, what was it, 1.20968. Yeah, 1.20968 times 10 to the negative 4. I prefer not to use the e notation for these things when I'm writing it down because it causes confusion. Well, so then, sorry, not t sub h, but t for now is ln of 0.76 divided by negative k. So here we go. Back to the calculator. I'll create a fraction and do ln of 0.76 and divide by negative alpha k. And there we go. 2,268.67 years. So 2,268.67 years. Now, I wouldn't expect for that to be really that precise. There's always some uncertainty, but this is a reasonable calculation given the information that we have. A couple of things to know about this. K is supposed to come out positive. And also the time that represents now should also come out positive. I found that students sometimes lose the minus sign somewhere along the way and get confused about that. So both the time that represents now and the value of the decay rate constant are supposed to be positive. Just to put this, to give a little more context, since 0.76 is between 0 and 1, its logarithm is negative. Remember, that's just a property of logarithms. So when we divide this negative number by this negative number in the denominator, the result will be a negative divided by a negative, which is a positive. So that's an algebraic way to see why the time is supposed to come out positive. And at any rate, this is the answer to the question that we're looking for. Okay, so there we go. That's an example of a half-life problem. Here's a doubling problem. A small colony of bacteria is growing exponentially in a test tube. At the start of the experiment, there are 8.2 times 10 to the 6th bacteria in the tube. 4 hours later, there are 1.4 times 10 to the 7th bacteria. What is the doubling time for this species? Okay, doubling time for bacteria. Okay, so first of all, let's get some intuition about these numbers. At t equals 0, that's the start of the experiment, and then t equals 4 is 4 hours later. At the start of the experiment, there are 8.2 times 10 to the 6 bacteria in the tube, and 4 hours later there are 1.4 times 10 to the 7. Okay, so I'm going to, this is actually going to be easier if I move this more directly on top of the dots. So how about this? Let me make this 2 times 10 to the 7th. So then halfway here is 1 times 10 to the 7th. 8.2 times 10 to the 6th is going to be right about here. 4 hours later, there's 1.4 times 10 to the 7th. So that's about here. And remember, this is exponential growth, not linear growth. So that's what the population looks like. Well, our goal is to find the doubling time for this species of bacteria. Well, what do we know about doubling time? Well, remember that there's a relationship between the doubling time and the growth rate constant. Do you remember what it is? It's ln of 2 over k. So if we can find the growth rate constant, we can use this formula to get the doubling time. So, all right, so we need k. Well, there's two ways to do this. First, let me sort of rederive the solving process for k. I'm going to start with exponential growth. So q is q0 e to the kt. We know that at time t equals 4, q is equal to 1.4 times 10 to the 7th. We are also told at time t equals 0, well, that's actually giving us q sub 0, which was 8.2 times 10 to the 6th. Let's fill in what we know. At time t equals 4, we're going to have 1.4 times 10 to the 7th for q. Then we're going to have 8.2 times 10 to the 6th for q sub 0. E2, well, we don't want to know what k is yet. We're going to solve for k. And then t is 4. That's because this number, the 1.4 times 10 to the 7th, comes at a time 4 hours after the start of the experiment. Now we need to solve for k. Okay, do you see how to do that? First step is to divide by 8.2 times 10 to the 6th. There is an exponential part, and we will need the logarithm, but not the first step. The logarithm will be needed here because at this point on the right-hand side, the natural exponential operation is the outermost operation. Okay. So we will apply ln. At this point, I believe I'm going to skip the intermediate step. I will write ln of the left equals, and I'll just go ahead and simplify ln of e to that stuff down to just stuff. Finally, we divide by 4. So that gives us k equals ln of 1.4 times 10 to the 7th over 8.2 times 10 to the 6th divided by 4. Let's go back to the calculator. Now you need to be careful to get the right components of this calculation in the right place. I'm going to start with a fraction bar and do ln of, and put in another fraction, 1.4, and just to demonstrate it, I'm going to use the calculator's E notation here. This is the engineering E that's right here, not the natural exponential E. So I do second and this to type the small capital E to get a 10 to the power 7 right there. Then I need 8.2 and an E and a 6 to get 10 to the power 6th. So that's ln of 1.4 times 10 to the 7th divided by 8.2 times 10 to the 6th. And the division is inside the ln. And then we divide by 4. Now since I'm going to be using this for something else, I'm going to hit the store button and hit the alphabet button and hit the parenthesis button to get K. So there we go. K is about 0.1337, which is a very leet number. Now that we've got K, remember what we're doing with this. We want the doubling time, and we need the fact that the doubling time is ln of 2 divided by K. Okay, so let us recall doubling time is ln of 2 divided by K. Let's go back to the calculator. Ln of 2 divided by K, and there we go. 183. So I'll just 5.18. Now as to what units is this in, if you look back at the problem statement, all the times that we were given were in hours. Well, there's really only one place here, 4 hours later. So that means time is measured in hours, which means that when you do this doubling time calculation, the result is going to come out in the same units. So that comes out in hours. So that's the answer that we're looking for. The doubling time is 5.18 hours. A way to sort of check this, give sort of a back of the napkin calculation, is that if you start with 8.2 times 10 to the 6th, and you double it, okay, so 8.2 times 10 to the 6th, and I multiply by 2, it's, well, we're going to have to count here. That's 1, 2, 3, 4, 5, 6, 7. So that's 1.64 times 10 to the 7th. So on this picture, what this is saying is that 5.5 hours, was it 5.5 hours? It was 5.18 hours. Okay, so not quite, not 5.5, 5 and a bit. So, you know, we let me see here, how much is an hour on this? I guess an hour, 5.5 hours would be about here. That's about where the doubling time calculation says the population should be after one doubling, about 5.5 hours. So that's conceptually the right order of magnitude, so it looks like we've done the calculation correctly. If we had gotten that the doubling time was going to be, 40 hours, then that probably indicates a mistake somewhere, because by 40 hours, just looking at these numbers, it looks like the population is going to be huge by 40 hours. Okay, so there you go. That's how to calculate the doubling time given 2 points on an exponential growth curve. Here's one more. A medication, a particular antibiotic, decays exponentially with a half-life of 7.5 hours. In a particular patient, the antibiotic is considered effective if at least 4 milligrams are present in the patient's body. If the patient is given a 10 milligram dose at 8 o'clock a.m., when will it cease to be effective? Okay. Okay, this one is going to have a couple of little complications. So, amount of antibiotic. This is presumably something where you either take a pill or they give you an injection. And we start out at 10 milligrams, and that's at 8 a.m. Now, just to give us some intuition, the half-life is 7.5 hours. So, if we go 7.5 hours forward from 8 a.m., okay, you have to be a little bit careful how you do time here. 7 hours and 30 minutes is 7.5. We can add this without having to do any minute carrying, and that takes us to 15:30, which is 3:30 p.m. Okay, so let's see what we got here. There's 8 a.m. How about we do 9, 10, 11, 12, so that's noon. And then 1, 2, 3, 4. So at about this time, the half-life will have passed and will have gone from 10 milligrams. Let's see, 1, 2, 3, 4, 5, 6, 7. So right about here is about half. This is 5 milligrams. So this is how much is left in the patient's body at 3:30. If I add another 7.5 hours, so I start with 3:30 p.m. and I add another 7.5 hours, we need to regroup some minutes here and rewrite this as 11 o'clock p.m. So let's see here, 4, 5, 6. So here's 6 p.m., 7, 8, 9, 10, 11, and here's midnight. At 11 p.m., yeah, that's right about here. Let me get another color here. How about brown? It will have cut in half down to about 2.5 milligrams. And now if I just connect the dots, this is what's supposed to be happening. We are told in the problem statement that the antibiotic is considered effective if at least 4 milligrams are present in the patient's body. We want to know, when does this dose cease to be effective? Well, just kind of eyeballing it, it looks like 4 milligrams is about here, and so sometime around then, looks like maybe between 5 and 6 o'clock, the antibiotic will cease to be effective, because down below here is ineffective. So we're looking for the first time t that the amount of antibiotic in the patient's body reaches that threshold of 4 milligrams. Okay, so here's what we're going to do. I'm going to let t equals 0 be 8 a.m. This is t equals 7.5 hours later. We are told that this drug experiences exponential decay. So there we go, exponential decay formula. We are told that the half-life is 7.5 hours. So that's the half-life on the t-axis. And we are told that the initial dose is 10 milligrams. So that's Q sub 0 equals 10, and we'll just do all of the quantity in milligrams. We want to set up something that means that the amount of medication in the patient's body is 4 milligrams. What kind of equation should we use? Okay, we want 4 milligrams equals, and it's Q that's the quantity of the drug in the patient's system. So remember, this is the t-axis and this is the q-axis. So we'll set Q equal to 4 and solve for what time t corresponds to Q equals 4. Okay. Again, there's this K in the exponential decay formula. The problem, sometimes these problems will give you the decay constant, but oftentimes they give you the half-life just because that's a more intuitive number to work with. So the thing to keep in mind is, did the problem give you a half-life or did it give you a rate constant? And if it gave you a half-life, maybe you should solve for the rate constant. Do you remember how to solve for K if we know the half-life? We need this formula. K is ln of 2 divided by the half-life. Again, this is going to result in some clumsy decimal number, and rather than write that out over and over again as we solve, it's usually better to just remember, okay, we know how to get K. I'll just write everything in terms of K and go from there. Okay, so let's fill in what we know. We'll solve for T, leaving K in place, and then use this calculation at the end. Okay, so Q is 4, right? Equals. Then Q sub 0 is 10, that's the initial dose, times e to the negative kt. Now we need to solve for t. Well, what should we do first? We'll divide by 10. So that leaves us 4 over 10 equals e to the negative kt. Now what? We need to apply the logarithm function. That will give us ln of 4/10 equals, and when we do ln of e to the kt, remember the ln undoes e to the power and will leave us with just the stuff up in the exponent. We're now trying to solve for t, so we should do what? Let's divide by negative k. So that leaves us with t equals ln of 4/10 divided by negative k. So once we've calculated k, we can use this to get the time that we are trying to solve for. Okay, so let's go back up here and return to the calculator. Let's clear out that problem. The half-life is 7.5 hours. I'm going to do this left to right. So ln of 2 divided by 7.5. I'll hit the store button and then the alphabet button and that button to get the K. So there's the decay rate constant, 0.09242. Okay, I wrote that down on the problem here just to have it for the record. What we're really interested in is ln of 4/10 divided by negative k. Well, 4/10 is easy, that's just 0.4. And then we divide by negative alpha k. And that tells us t is approximately 9.2 Okay. So again, what I was doing there, we filled in the K using this formula and the half-life that we were given. Again, the units of this problem, time is always measured in hours. So this time that we've solved for comes out in hours. So you can, if you want, write in hours since the first dose. If we really wanted to give this as a specific clock time, well, all right, 9.914 is 9 plus, and we need to represent 0.94, sorry, 0.914, the fractional part of the hour, as some number of minutes over 60. So to solve for this m, I need to multiply by 60. So that gives me m equals 0.914, times 60. So the minutes would be 0.914 times 60. So that's 55 minutes, let's say. So that means that if we wanted to get a clock time, we could take 9 hours and 55 minutes and go forward from 8 o'clock to 9 hours and 55 minutes. Okay, so here we go, 8 o'clock a.m., and we're going to add 9 hours and 55 minutes to that. The minutes are no problem, and we don't need to regroup. That takes us to 17:55, and you subtract 12 from the 17:55, and that comes out to be 5:55 p.m. So depending on the situation, yeah, I guess I should write that. One or the other of those is probably what a problem like this would ask for. And I think for a problem like this, if I were to give it on an assignment, I would accept either of these. Again, returning to the picture that I drew, if you look at just these back of the napkin calculations, just drawing some pictures, the time that we were looking for actually comes out to be, it looks like, right there, a little before 6 o'clock, and we came up with 5:55. So that's a good check that we've done these calculations correctly. Very often, if you're doing this kind of problem and you make a mistake in a calculation, the next thing you do will be way off because you're dealing with exponential growth. So the fact that these back of the napkin calculations that we started with are lining up with all of this algebra, that's a reassuring sign that we've done things correctly. Okay, so that is the antibiotic decay problem. Incidentally, this is why when you take antibiotics, for example, they don't just give you one big pill. Instead, they want to maximize the amount of time you spend with an effective level of the drug in your body. And so rather than give you, one ridiculously large dose here at the beginning that might be dangerous, instead what they do is they give you a small dose, and then they know about what time it'll cease to be effective, and they have you take the next pill then, and then you take the next pill so many hours later, and then eventually you get to this part where you're taking a pill regularly and you're getting a long stretch of time during which the antibiotic is effective. For example, a Z-Pak. That's azithromycin, and it comes in a sequence where you take a very high dose to start with, and then you take a lower dose as you progress through the treatment, and it gives you a picture that looks a little more like this to start with, and then as you take the lesser doses later, it goes down like that. And this big dose is to clear out a big chunk of the infection, and then this dose the remaining pills are effective for clearing out a lower level of infection. So this exponential decay of chemicals is why treatments are given the way they are. Okay, so there you go. Exponential growth and decay, and a variety of solving techniques.